So good morning after the coffee break. I hope you are charged with new energy. And it's my great pleasure to announce on this session 3 great speakers. The first one is a godfather of quantum chemistry in Spain. So Manuel Yáñez, and he will be talking about interactions between electron-deficient systems and in particular some interesting peculiarities. So Manuel, the floor is yours.
Thank you very much. I would like to start thanking the organizers for inviting me to this nice conference and giving me the opportunity to come back to Poland, but it's my first visit to the capital, so I have to give particular thanks to Darek, because I met Darek many years ago when he came to Madrid as a master student in our European Master on Theoretical Chemistry and Computational Modeling, a master that was put together with the effort of 7 universities from 6 different countries: Valencia and Madrid from Spain, Porto from Portugal, Perugia from Italy, Toulouse from France, Groningen from the Netherlands, and Leuven from Belgium. And Darek was an excellent master student. And after that, we captured him as a very promising PhD student, very brilliant, and finally he proved that he was a very qualified researcher, but above all, he is a wonderful person and a good friend. That said, I must confess that I am nervous because I feel that I have a double responsibility, probably a triple responsibility today. The first one is that I don't want to deceive Darek and by extension all of you. The second one is that after the victory of the Spanish team yesterday in the European football competition, I think I have to prove that we are good not only playing football. But in this respect, I am a little bit too late because yesterday we have a wonderful presentation by David Ayuso on a talk dedicated to the chirality or possible chirality of Darek. And he clearly showed that this is the case because David is a researcher in UK, but was also a student of that master, and if my recollection is correct, he was in the same group as Darek because they are more or less of the same age. So he finished the PhD and well, that said, as Darek said, this is the title of my presentation, and I am not going to discover nothing new for you. Nowadays, theoretical chemistry, computational chemistry is able to simulate from small molecules to huge molecules like proteins in biochemistry or different kinds of macromolecules in the realms of material chemistry. And at this point, I cannot avoid to remember that exactly 50 years ago, in the highway between Pittsburgh and Washington, D.C., there was a huge panel announcing IBM that said, in San Jose's center, IBM San Jose Center in California, Professor Enrico Clementi is carrying out the first ab initio calculations on pyridine molecule. Well, the first ab initio calculations in pyridine molecule in 1974. Hartree-Fock calculations, okay? Because at that time, Moller-Plesset was not programmed yet by Popel's group, so we're just ab initio calculations. Nowadays, we are able just to study and to model quite reliably many materials. But at the same time, high-level ab initio formalisms, in particular couple cluster singles and doubles parentheses triples methods, or composite methods like G4 theory, can reach accuracies smaller than 1 kilocalorie per mole. intrinsic errors that are around 3 kilojoules per mole. And that opened the possibility of simulating and reproduce accurate experimental measurements in different fields, knowing that the calculations provide reliable results in those topics. Perhaps many of you are thinking, well, what is new about electron-deficient systems? You know, during many, many years, people was studying them theoretically and experimentally, so we cannot expect many surprises. However, I try to convince you that this is not the case, because they still hide some interesting and unexpected properties or changes in the intrinsic reactivity that would be just behind questions like this. Is it possible to change a conventional base into a strong acid? Or alternatively, it is possible to change a conventional acid into a strong base? Well, I will try, as I said, to convince you that that is the case, and that precisely electron-deficient systems play a crucial role in that sense. Well, in what follows, I am going to use different theoretical formalisms that I am not going to include in my discussion. In general, my energies will be obtained at the G4 level or at coupled cluster simples and doubles and triples, and in some cases using different DFT approaches, but I mention here the MO062X true large functional because in our experience is the one that gives better correlations with high-level ab initio calculations. Better correlations means linear correlations with n slope of 0.99, which is really something important. In order to understand the origin of, for instance, stability trends, are particularly useful different energy decomposition formalisms. We have used in particular two, the many-body interaction energy that allows you to split the interaction energy between two or more systems into one-centered terms, two-centered terms, or three-centered terms. If you are going beyond trimers, you can also include four certain terms, etc., and so on and so forth. The one-centered terms actually measure the distortion that the monomers in the interaction undergo after the interaction. And the second term, the second and third, the two and three body terms measure more or less the enhanced stability that you can get because of the interaction. A second partition scheme that is also very useful is the localized molecular orbital energy decomposition analysis, in which you are not looking at this kind of splitting, but to measure what is the proportion of electrostatic versus exchange versus polarization or versus dispersion contributions to the total interaction energy. Finally, the electron density analysis, that is also very important to understand why a molecule has a certain structure or how a molecule reacts in a certain manner. We have used four formalisms that are really complementary. The quantum theory of atoms in molecules is based in analysis of the topology of the electron density. You look at the topology of the electron density and you try to locate critical points in that electron density, first order, second order, third order. The first order points give you information about the characteristics and the strength of the molecular, the chemical bonds you are in the system, and you call them bond critical points, and so on and so forth. The electron localization function allows you to partition the whole density around a molecular compound, molecular cluster, in areas in which the population is maximum. and then allows you to classify these areas in monosynaptic, trisynaptic, or trisynaptic, attending to the nature of the molecular orbitals in which the electrons are located. So monosynaptic bases are typical lone pairs. The synaptic bases are typically covalent bonds between two atoms, but you can have also three synaptic bases, and I will talk about that in a moment. Then another alternative is the adaptive natural density partitioning, that is a formalism in the realm of the MBO, and also very important is the non-covalent interactions analysis that has been developed in particular very much by Julia Contreras in Paris, that permit you to see the areas of very weak interactions between two components. So areas in which the QTM or any other methods don't see anything, you don't have bond critical points, you don't have disynaptic, monosynaptic or trisynaptic areas, but still there is an interaction. In most of the cases due to dispersion or to another interactions that can be visualized with the NCI. Well, electron-deficient derivatives have a peculiar chemistry, and this peculiar chemistry is directly related to their capacity to behave as strong Lewis acids. So the electron-deficient systems interact fast and efficiently with Lewis bases, with compounds that can donate a lone pair to the electron-deficient one. And I like this picture, that is very beautiful, that is a paradigmatic example of what I'm saying, because in this experiment you are putting together in contact two colorless gases, ammonia in one side and boron 3-fluoride on the other. And then you see that there is some smoke forming, that is not smoke, is tiny white particles that corresponds to a new compound, in which you have a new bond between the nitrogen and the boron. It's not a typical covalent bond, because you are not sharing a pair of electrons with this part of the charge that is donating from the lone pair of the nitrogen to the empty orbital of the boron atom. Historically, the bonding peculiarities of the dimer of borane is a page very interesting in the chemistry of the 20th century, because for many years nobody was able to explain why the dimer has this structure. But molecular orbital theory found the answer, because in this case you have the formation of new molecular orbitals. In general, when you start with a hydrogen molecule, you have a molecular orbital formed by the combination of the atomic orbitals of the two atoms. But in this case, you have a molecular orbital that is the combination of one p orbital in boron, another p orbital in the other boron, and the one s hydrogen in the middle. So you have a pair of electrons located in an orbital that is three-center to electron bonds. And that is the picture. So you see that you have one of these orbitals here and the other orbital here. So you have actually another concentration because of the overlap of these two orbitals. When you look at the Q-times picture of the system, you realize, well, immediately, these distances are, of course, longer than that one, because here you do not have a normal covalent bond. You have a pair of electrons bonding three atoms and not two. Well, that is normal. When you look at the density, you realize that the bond critical points between the boron and the hydrogens that bridge the two borons are, oh, sorry. Well, are bent like that, are not linear like a normal covalent bond. And that is because it's reflecting this fact, the fact that now the electron density is not strictly located between the two nuclei, but more or less concentrated in the middle of the ring. Well, that is well known. But if you are interested in continuing with the bonding characteristics of the system, and you go simply from borane to trifluoroborane, and you look at the structure, what you see is this. Well, looks like diborane, you know. You have here a fluorine that is bridging between the two boron atoms. But this is not a local minimum. It's a transition state. So when you try to follow the displacements associated with the imaginary frequency of that transition state, what you get is two separated BH3 systems. The monomers fall apart. And for many years, this was assumed as the reality. So you can read many papers that said these dimers do not exist. But they do. The dimers exist, and these are the structures. When you calculate these dimers using an appropriate theoretical model, not a DFT model, but for instance a couple cluster procedure that accounts for dispersion, what you get is this. When you look at the geometry, most of the programs give you this picture, you know, with a bond between this fluorine atom and the boron. And actually you think, well, that is logical. You have electron density on the fluorine atom, negative charge interacting with the boron that has a hole. But when you look at the topology of the electron density, you see that there is only one bond critical point, and it's between the two fluorine atoms, not between the fluorine atoms and the boron. And when you look at the non-covalent interaction, you see exactly the same. You see there is a blue region here, which is a weakly attractive area, and the green areas that are slightly repulsive. So you have only an attractive interaction between the two fluorine atoms. It's a weakly bound species, but it exists. But it's even more curious when you move. Oh, and if you carry out the LMBO analysis, you find that the dispersion accounts for more than half of the interaction energy in this particular case. But when you move to the trimers, it's even more surprising, because triborane is a quite stable cluster, you see? 195 kilojoules per mole with respect to the isolated trimers. The fluorine derivative is unstable, is less stable than the separated monomers. It's a minimum of the potential energy surface, but that lie higher in energy than it should to be. And there is again a weakly bound trimer that is stable with respect to the monomers. Well, when you look now at the electron density distribution, in this case you find that there are three center 2 electron bonds, as in the dimer, with charge densities which are significantly large, smaller of course than in a normal covalent bond, but still significantly large. When you go to the fluorine case, the picture is the same. You have a strong boron-fluor linkage here, but also quite a strong boron-fluor with the fluorine that makes the bridge. While here, the interaction is again very weak. But this is not stable, and this is stable. So when you look at that, how this can be unstable and this can be stable? Well, you cannot forget that the monomers, the isolated monomers, are strictly planar. Okay? So boron has an sp2 hybridization. And the p orbital that does not participate in the hybridization and is empty is perpendicular to the plane and is the LUMO, the lowest unoccupied molecular orbital of your system. When you go to the dimer or to the trimer, the hybridization of this guy has to change. The system is not planar anymore because these two fluorine atoms or the two hydrogen atoms or here are in a plane perpendicular to the plane defined by the boron and the two hydrogen atoms. And that implies that is quite logical from the basic quantum chemistry. You have a planar system with a p orbital empty. The other molecule arrives, transfer some charge. The charge has to go to the empty orbital necessarily, and then you change the hybridization of your system from sp2 to sp between 2 and 3, and your system becomes pyramidal. But still, why this thing happens? Why this is not stable, this is stable, and this is stable? Well, this rehybridization, of course, have a cost, an energetic cost that is not at all negligible. So when you look at the MBI partition, you see that this cost is quite high for the hydride, but much higher for the fluoride. And then this next question is, why? Well, the cost you have to pay depends on the gap homolume, because you have to mix this guy that is empty with electrons with this guy that full of electrons with this guy that is empty of electrons. But the gap in the hydride is much smaller than the gap in the fluoride, because fluoride is very electronegative, so the HOMO is very low in energy, and actually the hybridization energy you have to pay to pyramidalize BF3 is 94 kilojoules per mole. In the fluorine derivative is 169 kilojoules per mole, and that is due to the fact that the HOMO-LUMO gap in the fluoride derivative is almost 40 greater than in the hydride. So what happened? You have two center and three center stabilizing terms, but in this case they are not able to counterbalance the high cost of the rehybridization. When you go to the other case, to the other cycle we have here, you see, in this particular case, the three monomers are planar as they were in the isolated case. So when you look at the results in the MBI, you see that the distortion of the monomers is practically zero, and even though these energies, stabilizing energies, are very small because the interaction is very weak, is dispersion, your cluster is stable in contraposition with the other one. Well, the situation changed significantly when you go to aluminum, because in aluminum, the trimer, the fluoride trimer, is perfectly stable. And it's perfectly stable, among other things, or basically, because the nature of the interactions have a much larger electrostatic component. Aluminum behaves more as a metal than boron, of course, and then you see that in the molecular graph, in the sense that the Laplacian, in the case of the hydride, is negative, indicating that these interactions are essentially covalent, but in the case of the aluminum, they are positive, indicating that here the interaction has an electrostatic dominant character that is also in agreement with the LMBO-ED analysis. Well, not surprisingly either, the stabilization of the diborane is larger than the stabilization of the DLA. But when you go to the trimers, the stabilization reverses. And now the trimer of the boron derivative is less stable than the trimer of aluminum. And the reason is because boron is not able to pentacoordinate. So when you have boron atom, around it you have only 3 ligands, and it doesn't matter if you try to put more, because the system evolves always to elongate that interaction. Whereas in the case of aluminum, for 2 reasons, because the interaction is essentially electrostatic, and because the size of the atom is larger and the bond distance is 2, is pentacoordinated, and that explains its enhanced stability. Well, the dominant electrostatic character goes higher if you move to the previous group in the periodic table, because not only boron, aluminum, the trial elements are electrodeficient. Alkaline earth systems are even more electrodeficient. So when you go and look at the structures of the dimers of beryllium dihydride or magnesium dihydride, you still see that the structure of the dimer is stabilized by 3 center 2 electron bonds, because you see here is a basin with a population of 2 electrons, here is another basin with a population of 2 electrons, but this basin is a disynaptic basin, it involves only the orbitals and the hydrogen atom here and the beryllium, but this one is trisynaptic, involving orbitals of the 3 atoms. And the same happened in magnesium. But when you move to the fluorine atom, the picture changes completely, because now the red basins are monosynaptic. So in the fluorine atoms, you have a basin that has a population, should be 6 electrons, because corresponds to the 3 lone pairs that have fluorine atom. It's less than 3 electrons because this charge is polarized due to the interaction with the beryllium atom. But you have these monosynaptic basins, and here you have not a trisynaptic but just a disynaptic basin between the other lone pair with the beryllium, with a population of around 1.4 electrons. But the question we wanted to analyze when we were looking to these systems was, what is the effect of the interaction between the Lewis axis and the Lewis base on the intrinsic reactivity of both components? So to analyze that, we have used 3 different bases, four nitrogen bases, from the saturated one, ammonia, to the unsaturated one, metanimina, HCN, and pyridine, which is aromatic, and also not only to study monomers but dimers too. The interaction in this case also lead to a change in the hybridization of the beryllium and magnesium atom. Is linear isolated, and here is bent. In the case of the dimer, is just has a typical sp3 hybridization. So this should change the properties of the system. Qualitatively, it's logical to expect that when this guy interacts with that base, the base is going to be a better proton donor. Why? Because part of the charge in the nitrogen goes to the beryllium, and then the nitrogen, which is more electronegative than the hydrogen, depletes part of the charge in the hydrogen, so should be a better proton donor. But quantitatively, is this really relevant? That is the question. Well, when you look at the bond dissociation energies of the different clusters you can form between beryllium dihydride with ammonia, imine, ICN, and NH3, these bond dissociation energies follow exactly the basicity of these molecules. The less basic one is ICN, the most basic one is pyridine, followed by the imine, and finally, and that's exactly the order you get here. Well, that is not surprising, but not surprising other is that the bond dissociation energies you have when you deprotonate your system increase significantly. That is not surprising either, because you are removing a proton from here, so a nitrogen atom is a much better electron donor. So this bond becomes, I pressed so enthusiastically the button, becomes much stronger, the distance becomes much shorter, and the stretching frequency is blue shifted. But these changes indicate that while methanamine is a better electron donor than ammonia, the corresponding anion is a poorer electron donor than the anion of the ammonia. So the neutral base, imine, is a better donor, but the anion is a poorer donor. Why? Well, that is because NH2 minus is a hard base, in the sense that all the excess of charge is located practically on the nitrogen atom, while in this case, in the imine, the negative charge is delocalized because you have here a double bond. And actually, when you look at the values of the populations, you see that in NH2 minus, the population in the nitrogen atom is almost twice the population you have in the nitrogen of the imine. But the more important thing is that the acidity enhancement is closely related with increasing the bond dissociation energies in the neutral and in the anion. Okay, you have the base. When you protonate the base, the value you obtain is what you call intrinsic acidity. You know, but if you now associate the base with BH2, you get a more stable system. The red values are for ammonia, the blue values are for imine. And now you deprotonate this guy, and the energy necessary to deprotonate this guy is much smaller because going from here to here, the stabilization is much larger. So the acidity you have here becomes much smaller because the difference is between these values and that values. So you go for more than 1600 kilojoules per mole to only 1400 kilojoules per mole in the acidity of the system. But nothing here is really new, because that was proved experimentally and theoretical for phosphoboranes in 2009. But if you go to the dimers, you can anticipate that the interaction of the base should be stronger, and should be stronger because now in the monomers you have the pi holes, where the electrons are going to be forming a belt with respect to the symmetry axis, and here are located on the beryllium atoms, but the depth of the hole is deeper. So this guy is a better electron acceptor than the other one. And actually what you see is the bond dissociation energy of the interaction between the dimer with the base increases. But what is relevant is that the increase in the deprotonated species is 4 times larger. What is the result of that? The result of that is that the acidity when you have a dimer is still 71 kilojoules per mole greater than the acidity when you have the monomer. So the acidity when you have the monomer is increased significantly, but when you have it is increasing further. Why is that? Well, the reason is very simple. That is the interaction you have between the base and the dimer in the neutral. But when you remove a hydrogen from there, you have not 1 lone pair, you have 2 lone pairs free on the nitrogen atom. And then you are able to form this new structure in the anion, where you have a new beryllium nitrogen bond, and therefore an enhanced stability of the system. The final result is that if you go from monomers to dimers, the acidity increase, and from dimers to trimers too. I don't have time to discuss this, but this increase takes you from 1600 to 1200 in the case of ammonia, and in the case of imine. 1219 kilojoules per mole is the acidity of sulfuric acid. So you have an ammonia molecule or imine molecule that is as acidic as sulfuric acid. But what is more impressive is that in the case of HCN, you have a carbon acid because it's the only proton you can remove, and his acidity is larger than the acidity of perchloric acid, that is the oxyacid stronger known. What about the basicity? Well, when you look at the basicity, there are 2 possible protonation processes. You can protonate the base, or you can protonate the BH group. When you protonate the base, you obtain this, NH4+, interacting with the hydrogen bond with the beryllium. When you protonate this, you have here a closed shell cation interacting with H2 molecule. This species is forming a hydride extraction reaction. So the basicity of this guy depends on what we call hydride honorability, the ability of the complex to liberate H-. The larger is this ability, the larger should be the basicity. But what is important is that this dominates on that. If somebody asked me before doing the calculations what would we expect, I would expect the proton to go there and not to go there. Why that? Well, if you look at this thermodynamic cycle, in the case of the hydrogen extraction, the first thing you have to do is to remove an H minus from here. And that is a very endothermic process because you have to break a bond. And now the hydrogen minus interact with the proton to form hydrogen, and hydrogen interact with this cation to give the final product. And the whole process is exothermic in 171 kilojoules per mole. When you do the other thing, you protonate on the NH3, the first thing you have to do is to break this bond. This energy is much smaller because it's a dative bond. Now you protonate the base, is the basicity of ammonia that is quite large and exothermic. But now the result is that this value is smaller than that value. And the reason behind is, in spite that this is a very endothermic process, this is a very exothermic one. And therefore this dominates over them. And this results in a huge basicity enhancement. You see, the basicity enhancements that are of the order of 230 kilojoules per mole. For dimers, the situation is exactly the same, but the basicity increased further. And therefore, what you have are increases of the order of near 300 kilojoules per mole, that in the terms of the ionization constants are increases of 40 orders of magnitude. When you go to the hydrides, the scenario changes, because you can have also an equivalent reaction, a fluoride abstraction. You liberate an Fn minus for here, you form the FH molecule and you get this structure. Or alternatively, you protonate the base and you have an interaction which is a hydrogen bond. But in this case, this is the most favorable process. What is going on? Well, again, the cycle explains you what is going on. This cycle is similar to the one we saw with the hydrides, an endothermic process to produce F minus, here an exothermic process to protonate NH3, which is the same. The difference is here. The formation of FH is much less exothermic than the formation of hydrogen. And therefore, now this dominates on that. And the basicity enhancement is still as large for the fluorides than for the hydrides. So, to conclude my presentation, there are three important factors that regulates the chemistry of electron-deficient systems. One is the rehybridization, and that is something that is frequently forgotten in the literature. You know, people talk about esoteric arguments, you know, like interactions in the sense that the substituents move of pyramidals just to make room for the bases to approach. No. In the BF3, the system is planar, so there is no spherical impediment for the base to approach. The guy pyramidalized because you are introducing charge in an empty orbital that changes the hybridization of the system. More important is the importance of dispersion, and it's important because in general this contribution is small, except in the cases I showed you, the trimers or the dimers of boron trifluoride. And that's a serious problem, because if you do the calculations using methods like G4, you are going to get the wrong results. Not because G4 is not able to account for dispersion, because it's based in a geometry that is wrong. Because in G4 you optimize your geometry at the B3 level and the B3 level, and this functional do not account for dispersion. So this functional gives you a wrong geometry, and now you make a very high level calculations on that geometry, and your results have no sense because of that. Well, the interaction between a Lewis acid and a Lewis base imply the perturbation of both, the base becomes a very strong acid, and the acid becomes a very strong base. And the enhancement implies changes in the ionization constant from 20 to over 40 orders of magnitude. And what is important, these effects increase with the increase of the size of the beryllium or boron cluster. It's larger for dimers than for monomers, it's larger for trimers than for dimers. And just to finish, let me thank the people that was engaged in all this work, Professor Otilia Mo and Merche Montero Campillo from my group, and Professor Ivonne Alcorta and José Elguero from the Spanish Research Council. And thank you very much for your attention. Sorry for these problems with the slides and things like that.
Thank you, Manolo, for the very nice presentation, and personally for the very good words about me at the beginning. It's time for questions.
Thank you, Manuel. It's always great listening to you. It's like coming back to the bachelor. And well, you always show that you are an excellent teacher. I have a question regarding the BF3. In this case, do you have the p orbital of the boron still empty, or you have some interaction between the p orbitals of the fluorine? Because I don't know if you have this energy gap because you have this electronegativity, or because you are forming some p bond between this boron and fluorine.
No, in the isolated monomer, the isolated monomer is strictly planar, and that is also the experimental evidence. Is strictly planar and perfectly symmetric D3H. So there are no interactions whatsoever between the fluorines, and the LUMO is actually an empty orbital perpendicular to that plane. As soon as you approach any molecule, it's not necessary to have a nitrogen base, any molecule able to release some electron density, this electron density has to occupy necessarily the empty orbital, and immediately the BF3 becomes out of the plane. If the interaction is very weak, comes out of the plane immediately, even if it is very weak, but the angle is still close to 120 degrees. But if the amount of charge you are donating is large enough, then the polymerization is critical. Then you can have also now interactions between the fluorine atoms, because the fluorine atoms approach each other because of the polymerization, and at the same time they are receiving more charge from the boron atom because the boron atom has also received some electron density from the base. So the picture changes completely. The electronic distribution of the boron atom changes, and the electronic distribution of the three fluorine atoms changes too.
Thank you.
So we have time for more questions.
It was amazing talk, thank you. I would like to ask about rehybridization timescale. Do you know something about this?
No. The only thing I can say, but it's a time that means nothing, is the first experiment I showed you. That as soon as you make a flux of ammonia with a flux of BF3, immediately you see this white smoke. So in lab time is immediate, but I have no idea about the real time of the interaction. But it's very efficient. It's very fast, but I think as far as I know, nobody measures strictly what is the real time of the reaction.
Okay, thank you.
But it's you put it together, immediately you see the smoke forming. Yeah. It's a question of I would say less than 1 second. So you open the two keys together at the same time, and immediately you see the white thing coming out, forming.
So are there questions? So maybe I can ask you one. So you showed like dimers, trimers, and this rehybridization and so on. Did you try like look into some cooperative interactions for bigger clusters and see the effect, how this can be affected if you go to a little bit bigger clusters, or?
No, that is a good question. I didn't talk about trimers, you know, and I didn't talk because I have a limited time and I want to make a general picture. When you go from monomers to dimers, the picture I show is quite clear. The dimer is a better electron acceptor than the monomer. But when you go to the trimer, it's not so trivial. Because when you go to the dimer, you have one boron here, the other boron here. So this boron now feels the effect of the other boron. And that is why it becomes more electro-deficient, because now it's sharing some charge with it. But when you go to the trimer, you have two kinds of boron atoms. The two streams and the one in the middle. And the one in the middle is the better electron acceptor of the three. But the depth of the pi hole is smaller than in the dimer. It's smaller. But there are new tautomers in the potential energy surface in which the three boron atoms are not linear. They form a cycle in which the three boron atoms are sharing the hydrogens. But this particular cluster is slightly less stable than the linear one. So strictly speaking, you have the linear trimer, the other one is less stable. But when you study what happened when the first one interacts with ammonia and the second one interacts with ammonia, the stability order changes completely. And now the cluster that was the less stable as a separate cluster becomes much more stable than the other, because you have like a cage. The three boron atoms form like a cage, so the electron density that is coming from the base distributed in that case and make it much more stable than the linear one. Our question is, what happens if you go to a tetramer? I don't know. Because I am guessing that it's going to be very, very complicated, because already the potential energy surface of the neutral is going to be much more complicated. The possibility of having different tautomers close in energy is quite high. But probably if we are enough crazy, we can go and look at the tetramers. But going from dimers to trimers is a whole story that could take me another 20 minutes just to explain it to you. But okay, I summarize it.
So thank you very much for this great talk. Thank you again, speaker.